So now let's go to the extended gamma filter. After we finish this linearization, you get the matrix here, start from your f, which is a nonlinear function. And what about the a? That's the Jacobian of the f. And this h is the Jacobian of the h. That's the Jacobian of the h. And now, a little bit different. What's the difference? Instead of look at the function, I look at the change. Look at the change. And that's nothing new. So the x accurate position equals the estimated position in the previous stage times the change from the estimate to the real position. And that is nothing more than this linearization. Yeah, here you go. What we are doing is nothing more than this. See, put this x position, that's the estimate, and the previous position, and then this two position equal the Jacobian times this change. This change is what I write down as xk minus 1 hat. This slide. Okay, here you go. That's the P0P, basically. But we always add the noise. That's why it's called the stochastic difference equation. Well, so what do we got so far? We changed the nonlinear error model into a linear error model. We changed the function into a linear transition represented by those matrices A and HK. So now let's go to the gamma filter. Very similar. If you really want to do the calculation, of course you need to know the F, which is the transition relationship, H, the measurement relationship, Q and R at the noise, the error. And we use that for the previous input. This is the estimate of the time t equal k minus 1 about the position. And this is the covariance in the last step. The only difference is you need to figure out this Jacobian of the transition, Jacobian of the measurement, and also the noise need to do a little adjustment. Similarly, we do the prediction stage. We use this k minus 1, talk about the a priori state estimate. That's in the prediction model based on the relationship of this h. And the pk, that's the a priori error covariance in the prediction model. When both put into k, and this really put into k, that's a posteriori state estimate, even afterward, after you do the measurement and the update. And so is this covariance, is the after update. So now we are ready. Once you get the symbols ready, okay, here you go. That's the algorithm. Look at the difference. What's different from what we learned before? First, different, you need to calculate the Jacobian in each step. In each time t equal k, you calculate the Jacobian. Second, when you do the prediction model, you use the nonlinear model. Of course, you know it. You know the function you plug in. You can always figure out your prediction based on the nonlinear model. In the estimate of covariance, same thing. That's the a priori estimate. What's the difference here? When you look at the innovation residue, you use the nonlinear function here. Nonlinear function. You have the h, you just plug it in based on your estimate of the position. What is your measurement? And the zk is your real estimate, your real measurement. And this y tail, they basically is the residue, or say the error, between your predicted measurement and the real measurement. That tells you how good is your prediction. But it depends on the noise of the measurement too. The innovation covariance SK is a middle step at the measurement noise, and add your use the a priori covariance here, and then you got this covariance. And then this will measure how good is your measurement. Now the K-mark game is the weight. How much you want to put the trust on your prediction. How much trust you're going to put on your correction based on the measurement. That game, KK, tell you that. And then your update, your correction is your posteriori estimate equals a priori estimate times the correction of the K-mark game times this innovation residue. That tell you how good your measurement. Well, in the final stage, you update your covariance. Same. So what is not the same? This step is new. This is slightly different because of the F. This is slightly different because of H. That's not linear. In your previous model, you're going to multiply the F here. You're going to multiply the H here, right? But you don't use the estimate. You use the real one. That's the difference. Okay, what are the differences? The other difference you have is you need to, let me put it this way, always put this little k, little k, little k, little k. Why? Because in each step, this matrix change. In the previous example, in each step, the matrix does not change. Again, let me look at the rotation. If your vehicle do a rotation all the time, you see when the time change, your rotation matrix, the cosine, see the rotation matrix is cosine theta, negative sine theta, cosine theta, and the sine theta. Because your t go to 0, your theta is also go to 0. A good approximation is the cosine theta always approximated by 1, and the sine theta approximated by theta. It changes, depends on the theta. But once you fix the k, the theta equal k is a constant. You can use it because how much angle you rotate it, you can put this like 1 degree, and then your matrix will become 1 approximately negative 1 over 360, that's 1 degree, and that's the cosine. Negative, that's positive, and that's 1. That's how you multiply. The comparison, what's the difference? You read it. The only two-step difference. One is you need to calculate the Jacobian in each step. Another constant, you have to have this little k because it changes. It's not a constant. Other than this, no difference. When it's going to be bad, it really depends how much on linear. One thing could be not linear like this. It's pretty much close to linear. It could be nonlinear as bad as this. That's very high nonlinear, right? So if it's very high nonlinear, your extended K-mark filter will not work well because you have the poor estimate of the covariance of this noise. Oh, by the way, linear simply means proportionally change. Nonlinear means you change not proportionally. Make sense? Okay. Well, the last thing is the example we showed in the first few slides about this function. How do we simulate this wave, which is x equal sine y t minus 1 and the y equals itself. In this example, all we need, in this case, x is the variable 1, x1 I wrote down before, and the that frequency is the y, x is this x. And then you can see the frequency at the time t equal the frequency at the t minus 1. The x at the time t equals the sine of the frequency times the sine of the frequency at t minus 1 times the time minus 1. Then you say, what? You said the frequency is a constant. Why you always need to put this t minus 1 there? What's that question? They all have the noise. They're not stable. They're not exactly what you expected. They always have error. That's what happened. Then in different time, they have different random noise. This random noise make them jump back and forth. So the real graph will show you everything. This graph is the position. x1 as the estimate is this green line. See all those things? You have 3 of them. If you look carefully, you have 3 of them. 1 in the top, 1 in the middle, 1 in the bottom. That's a sensitivity analysis. They put a little deviation to make 3 of them. Okay? That's the final result of your estimate. The purple one is the perfect line as a comparison. Means if everything is perfect. And all those data points, that's what the measurement is. Because the measurement has a big noise, W equal 1. That's why it bounces everywhere. So in that model, the weight is more like in the prediction. But you can change this weight into small, and then those points will be very close, and you get a different 3 graphs. The 3 graph is the perfect one, the measurement one, and the measured one, those red gram points, that's all point, and then the final Kmart filter give you that path you have. And this one, you remember the frequency is a constant. That's the frequency, perfect one. But in your simulation, in the beginning, you start with 0. That's what you estimate. And then you go back into here. And very soon, after 300 steps, it converges into the perfect line. Basically, the filter understand, don't need to change. Now I got the perfect answer. So that's a nonlinear model.